Thanks to the organizers as well for giving me the opportunity to speak here. It's my first slide talk, and it's my first talk at the conference. So I hope it will work out. It is a joint work with Meniaka, Philippe Michel, he's from EPFL, and Andreas Wieser. The first and the last one are both at ETH as well, and Andreas gave a talk on Monday. Yes, it is unpublished, but it's actually submitted already as part of my thesis. So it should be out in the next few weeks, days, we hope. I either get to talk about the proof or the setup, and talking about the proof without the setup within 30 minutes does not make a lot of sense. So I will mostly describe why it is a problem in homogeneous dynamics and how we attack it. But at the risk of not being able to mention that, I want to state two, in particular, one crucial input to this work is similar to what Andreas talked about, is the joinings classification by Einsiedler and Lindenstianss, which was published this year, but which was available on arXiv for quite some time. The joinings classification for certain diagonalizable higher rank actions on S arithmetic quotients. The other crucial input was mentioned by Andreas as well, is the near equidistribution of large toral packets of torus orbits in quaternion algebras. Good. So now that we have that, let's get started. I want to remind you what an elliptic curve is. For the sake of this talk, it suffices to assume that the characteristic does not equal 2 or 3. In this case, our result is easy. And for simplicity, an elliptic curve is the locus of this polynomial equation where the coefficients have to satisfy a certain condition. This is related to the discriminant of the elliptic curve. In fact, it's a projective variety, so we add one point at infinity, which, yeah. This point serves also as the identity in the abelian group that the elliptic curve is. As E is an abelian group, there is some homomorphism from the integers into the ring of endomorphisms of this abelian group. And in fact, one can show that the ring of endomorphisms has characteristic 0. So it contains a copy of the integers. Okay? This is just to illustrate the proposition to follow. So if E is an elliptic curve, then there is a trichotomy. Either the endomorphism ring is precisely the integers, which is given just for clarification. If it's not clear, if you have an abelian group, you can map G to NG, which defines an endomorphism, and this always exists. So this is, in some sense, the trivial case. Or the endomorphism ring is an order in an imaginary quadratic number field. Think of the ring of integers in a quadratic imaginary number field, like the Gaussian integers, the adjoint imaginary unit. In this case, one says that E has complex multiplication. Okay? Then there's the third option, where the endomorphism ring is an order in a quaternion algebra. Quaternion algebra is a 4-dimensional Q vector space equipped with a multiplication and which is simple. The center is precisely a copy of the rational numbers. I think that's it. And an order in there is a similar thing as an order in a imaginary quadratic number field. You should also think of integral structure, an integral lattice, a rank 4 Z module, which is also a ring and contains the multiplicative unit. Let me see. There are two quaternion algebras you should think of course, the Hamiltonian quaternions and the 2x2 matrices. The 2x2 matrices are a quaternion algebra over every field, and it's a so-called split quaternion algebra. Good. Then moreover, if the characteristic of our field over which the elliptic curve is defined is 0, then there are only two cases. Either the endomorphism ring is in that sense trivial, or it is an order in an imaginary quadratic number field. I come back to that on the next slide, I think. If the characteristic of the field is positive and E is supersingular, that is, this is the endomorphism ring, then one can show that E is isomorphic over the closure of Fp to a curve defined over Fp squared. One has to take a quadratic extension. In particular, the set of supersingular curves defined over the algebraic closure of Fp, the set of isomorphism classes is finite. There are only finitely many equations, right? There are only finitely many possible coefficients. Good. So we have a fixed set for each prime, we have a fixed set P which is finite. Okay? And one can say how many there are, but that does not matter for this. So I come back to elliptic curves defined over C. And the crucial point is by this Gaga correspondence, géométrie algébrique, géométrie analytique, there is a correspondence between an elliptic curve. So the C points of an elliptic curve correspond to this quotient where lambda is a lattice in C. Okay? This you do via the Weierstrass function. So there is a one-to-one correspondence between, this is even more crucial to us, there's a one-to-one correspondence between lattices up to C homothety, that is stretching and rotation, multiplication by a complex number, and elliptic curves defined over C up to isomorphism. And we introduced before, we said there are two cases. There are, for a curve defined over C, it either has endomorphism ring equal to the ring of, to the integers, the rational integers, or an order in a quadratic number field. These curves were called complex multiplication curves. So for the talk, you should think of D as being a fundamental discriminant and OD being the ring of integers with this discriminant. That is, this is the quadratic imaginary number field. D is a negative number. And this little fractal OD is the ring of integers in this number field. And then we denote by, or I denote by CMD, or we denote in the paper, by CMD the isomorphism classes of elliptic curves which have endomorphism ring precisely this ring of integers. Okay? And it's under this description we had up here. This is not a surprising set. So there is the class group associated to the ring of integers, which is the, let's say, the set of fractional ideals. Set of fractional OD ideals up to equivalence, that is a principal correspondence, up to multiplication by an element from the field. And the correspondence is, now if you view this field as a subset of the complex numbers, under an embedding, you can send an ideal A, which is a subset of the number field, to a lattice. This is a statement. This is a lattice due to Minkowski, if I'm not mistaken. And so we can associate to the ideal this quotient, which is an elliptic curve, and the C isomorphism associated. So this is isomorphic to all the elliptic curves we get if we change the representative in this ideal class. So these are precisely the complex multiplication curves, and of course, the ideal A has complex multiplication by the ring of integers. Okay. Let me point out. So this is nice. Now this we don't need anymore. I think this is clear. So this guy, the cardinality of the class group is grows with the discriminant. This is due to Siegel's lower bound. Okay? So there are way more complex multiplication curves than there are supersingular curves for a fixed prime at some, for large enough D in absolute value. Good. So let me think. Okay. I need to introduce something. How much time do I have? Still have plenty of time. So we denote by this guy, if we want the Q points, we denote by the symbol the quaternion algebra defined over Q, which is ramified precisely at the infinite place and at the p-adic place. So much more easily, for all rational primes Q, which are not infinite or equal to P, we have the quaternion algebra at, or Q is not a good letter. Let's use L. This guy is isomorphic to the split quaternion algebras, the 2x2 matrices with entries in QL. And these places, these ramification places, uniquely determine the quaternion algebra. So this will be the notation for the rest of the talk, and O is a maximal order. Rank 4, Z, module, which is a subring. So in this case, for supersingular curves, we have a similar one-to-one correspondence. So the supersingular curves, which are defined over the algebraic closure of Fp up to isomorphism, are in one-to-one correspondence with the class set of this order. So similarly to the ring of integers, there's a notion of a class set. It is not a group in this case. And we can also look at the left O ideals. So because of non-commutativity, it matters on which side we multiplied. And on the right, we can change it by a unit in the quaternion algebra. And to realize this correspondence, if you fix an elliptic curve whose endomorphism ring is this maximal order we started with, then the correspondence is given by sending an isomorphism class of such a supersingular curve to the set of homomorphisms from this elliptic curve to our reference elliptic curve. Okay? Good. This is in, yeah, if you now post-compose this with an endomorphism of E0, this is an ideal. Good. So the next statement to make is if we have a complex multiplication curve defined over C, then it can actually be defined over a number field, a finite extension of Q. And if the prime P is not split in this number field, then there is a reduction map, which maps our complex multiplication curve to a curve which I call E mod P. It's not a precisely reduction of coefficients mod P. You have to choose a prime in the number field, and it's a bit more complicated. But anyway, this curve we obtain is supersingular. So we have a mapping. The crucial point is we have a map which goes from the set of complex multiplication curve to the supersingular curves, in particular from a relatively large set to a set of fixed size. And so we fix a reduction. We call this the reduction of E. We fix such a reduction and the maximal order associated to it in this quaternion algebra. There's a fact that this one lies precisely in here. Then we can do a similar reduction of coefficients, which is again a bit more complicated, to reduce the endomorphisms of our complex multiplication curve and embed them in the endomorphism ring of the supersingular curve. In particular, we obtain an embedding of our ring of integers in this maximal order. There is some choice involved here. We have to, this isomorphism has to be normalized, and so there's some technicalities which I don't want to get into. Excuse me. Good. I think we have everything to state the theorem. Yes. So this is the theorem we prove. Meniaka, Philippe Michel, and Andreas-Wieser. We fix ourselves two odd primes and some more primes. These two play a special role. This one will be the ones for the supersingular reduction. So we fix ourselves at least 3 primes, distinct and odd. Then there is some negative number such that for any fundamental discriminant which is less than this number and for which the primes P1 to PS are inert in the number field and for which Q1 and Q2 are split in this number field, the map which sends a complex multiplication curve to the tuple of all its reductions with respect to these S distinct primes we chose is surjective. If we only have one prime, this was proven by Philippe Michel, I think, without splitting condition, because it works very differently. So what is the splitting assumption? This has to be pointed out. This is a splitting condition. It is what we use, as I said, is this classification of joinings of higher rank diagonalizable actions, and these 2 primes give us 2 fixed split places where we have, so that we get the action we want. In fact, we do not prove that it is surjective, and also Philippe Michel did not only prove that it is surjective, we prove an equidistribution result with respect to a natural measure on this set of supersingular curves. So we take the normalized counting measure and look at and show equidistribution. Good. For what follows, this group is the projectivized, denotes the projectivized units in the quaternion algebra, which is a algebraic Q group, and so on. And one can show that this class set has a homogeneous description. Luckily, I don't need to introduce the adels anymore. So here, these are, this is just the finite adel points, no infinite place. This is the Q points, and this guy here, so if O is this maximal order, then I can complete it. I can look at its completion at a place P. And I can look at all these completions as a sequence, and this is what I denote by O hat. And then we take the units thereof and we projectivize them. This is a compact open subgroup of this guy. It's similar to the Z hat, points of PGL2 in PGL2 finite adels. And this, as argued, is in one-to-one correspondence with the class set. So if we now fix our if we now fix our primes, which we assume to all be at least 3, and if we fix ourselves a complex multiplication curve and denote by OI the endomorphism ring corresponding to the elliptic curve after reduction with respect to pi. So for each prime we fixed, we get an endomorphism ring, which is a maximal order in one quaternion algebra. Then we obtain this map. So we have a complex multiplication curve. We send it to the tuple of its reductions, and by this correspondence here, we send it to the product of these quotients. Okay? And these quotients I will denote by this curly xi, where I stands for the choice of the prime. And in particular, we have this induced diagonal map. Okay. So if we have any such embedding, then it is completely determined by the image of the square root of D, because the field is two-dimensional and the rational points are eliminated under the map. We will denote by T iota the image of all the units in the quaternion algebra which commute with this particular vector. And the image of all these units in the group of projectivized units. And we have to choose a compact open subgroup of this torus. This is again, this is a Q anisotropic Q torus, and we choose a compact open subgroup of this torus by intersecting it with the compact open we had in the ambient group. One can show that this double quotient is actually the same as is isomorphic to the class group of the ring of integers, and hence we have this correspondence of complex multiplication curve to this homogeneous space. Later, if we drop the f in this notation, then it means that we also include the real points. So if we start off with an ideal class and choose a representative in this double quotient of this ideal class, by what I just said, by the correspondence, we can define a set-valued map, which maps the ideal class to the orbit of the identity coset translated by this representative and under this compact open part of this torus. Okay, this is a set-valued map. It's handy to illustrate what I want to do. So we again have these primes, and then we obtain a map which goes from the complex multiplication curves, which are in one-to-one correspondence here, to subsets of these quotients. I only take the left quotient, and then we can project. We take the right quotients again. So we have this map. And the crucial part is that these two maps agree. So whether I go in this algebraically defined association or whether I do this homogeneous construction, we obtain the same reduction. And this is what gives rise to the theorem that we prove. So I'm close to finishing. Let me say, so combining this homogeneous description we now have of the problem with the classification of joinings by Manfred Einsiedler and Ergodic, the near equidistribution of large torus orbits in so in the notation that you have now seen, if you take this guy and you have this embedding depend on the discriminant, as the discriminant goes to infinity, the push forward of the invariant measures on the quotient of this guy to this space has as weak star limits only measures which are invariant under the simply connected, under the image of the simply connected cover. There is some technicality. This is the image of the norm 1 units. And then in addition, we show that these large torus orbits equidistribute if we project them down to the, if we take the quotient by the projective units in the maximal orders. So if we cut out by this open compact subgroup, and then the theorem follows. I think that's where I should stop.